Hi, we are GTU rover team from Gebze Technical University in Turkey. My name is Emre, and I am the team leader. Based on the previous experiences from the last year, the new rover has been designed and manufactured to tackle URC competition tasks. The subsystems were analyzed in simulations and tested on each task to ensure all the requirements are met. After 8 months of hard work, we are proud to introduce our next generation rover. The earliest stage of the system design, durability and reliability have been considered. Sheet metal body is mounted on a link tracker system. Aluminium linkage allows the wheels to actively conform to the terrain, producing a more efficient drive. The wheel assembly consists of two main parts, the 3D printed rim and the motor housing parts. The pneumatic tires absorb shocks caused by falls, thus preventing the electronic parts on the rover from being damaged, and also improve the traction. Powerful geared DC motors are used to help the rover climb steeper slopes in the extreme retrieval and delivery mission.
To interact with mechanical and software parts of the rover, we have developed our next-generation electrical system. Custom-designed PCBs let us easy integration and plug the cables. For ensuring the safety of the rover, two emergency kill switches are installed. The communication system operates in the 2.4 GHz band, along with omnidirectional antenna on the rover and a sector antenna at the base station. The communication system is capable of data and real-time video transmission. In case of any connection loss, the backup module will be activated.
A 6 degrees of freedom robotic arm was developed to have manipulation capabilities. For high kinematic reachability, rotational actuators are used in all axes. In the first 4 axes, Warn-G mechanisms with geared DC motors are used to prevent back drive and provide required torques. The robot arm works precisely enough to manipulate the elements on the panel. A belt-driven differential wrist mechanism ensures better motion in the 5th and 6th axes. With the high torque joints, the robotic arm is strong enough to lift 5 kg payload at full extension. The control system and interface allows to operate the arm by inverse kinematics and switch between forward kinematics when needed. Spherical wrist design enables the arm to flip the switches and type on the keyboard smoothly. You can press on the side buttons and tighten after inserting the hex key to the screw. For the arm's motor driving, RoboClaw motor drivers with integrated PID controllers were chosen. Incremental encoders are used to read motor positions.
To perform autonomous navigation mission, ROS navigation stack was used. Point cloud data from Z stereo camera is downsampled with a voxel grid filter. The obtained cloud is used to generate the local map, and a 2D LiDAR sensor is used to generate the global map. After the maps are created, A-star algorithm is used to compute global path and compute local trajectory. Time elastic band approach is implemented. Z stereo camera and OpenCV library are used to be able to approach the gates and posts with detection of the ARCO tags. To pass through the gates, we have developed an algorithm that can find the position of the middle point of the gates in real time. In this way, we are able to give direction to the rover. The interface is a web-based React application providing mission control and data visualization. There are customizable layouts according to the mission. They allow remote monitoring system state, streaming camera feed, monitoring of the sensors, publishing waypoints, robotic arm joint states and joint control.
The science team search for different types of life detection analyzes and integrate them on board. 3 separate scoops are linearly actuated to collect soil samples without cross-contamination. After that, the collected samples are transferred through plastic pipes to the test tubes in the FTIR spectrometer. We prepared our samples to mimic Martian soil, and with them, we optimized ATP and DNA detection assays to get the best results. With a custom Fourier transformed infrared spectrometer, we aim to analyze the type of molecular bonds in the sample to detect the presence of biosignature molecules. Team aims to identify traces on the rock surface and determine if it's related to life or a rock's mineralogical property. A deep learning-based algorithm was developed to have a match between the rock images from the cameras and the dataset created by the team. A set of sensors were integrated to observe the environment and evaluate the test results from soil analysis correctly.